Hi, I'm Teshcler, Executive Editor of Design World Magazine, and today we're going to tear down a clever little device called the Leap Motion Controller, which comes from a company called Leap Motion. Now, the Leap Motion Controller has gotten a lot of press because it lets users create effects resembling those in the Steven Spielberg movie Minority Report, where Tom Cruise controlled a computer just by making hand motions in the air. The motion controller itself is just about the size of a cigarette lighter. It sits on your desk and uses two small vision sensors to detect when hands float above it. The Leap's controller isn't just for moving around the cursor on your computer screen, though. There are some pretty cool apps that have been written for it. One lets you pull stars around in a star field displayed on your screen, and in another one, a school of fish follows your hand if it moves slowly. Waving your hand violently scatters them. And I've even seen one app that lets you control an industrial Scar robot arm with hand gestures. Now, there are a couple of teardowns already on the web that go through taking the circuit boards out of the enclosure, so we'll skip that part of the procedure and get right into what's on the circuit boards. There are two boards in the controller. A sponge rubber spacer lies between the top board and the transparent plastic cover. Pull that off, and you'll see the top board in all its glory. The most critical components mounted on the top of the board include the three infrared LEDs here, here, and here. These are what the motion controller uses to illuminate your hands so it can keep track of them with the vision sensors. Here. One interesting aspect of the LED mounting is that the two side LEDs here and here, each sit on small platforms of PCB material, so they are each about 1 millimeter higher off the board than the center LED. I'm not sure why. I thought initially this might be a way of angling the two side LEDs so they converge somehow, but a closer inspection of the little PCB platforms on which they sit shows there's no angling to them. So it's a bit mysterious, at least to me. If anyone has other ideas about this, I hope they chime in on the comments attached to this video. Anyway, moving on, also visible on the top surface of the top board is a flash memory chip here, and a crystal tuned to 32.768 kilohertz here, according to the markings. Now, the processor on this board, which isn't mounted to this side, has an input for a Watchdog timer which runs at 32 kilohertz, so we might surmise that this crystal might be part of the Watchdog timer. Now, a word about Watchdog timers. For those who may be new to computer technology, a Watchdog timer is generally just a signal coming into the computer chip that's used to cause a reset. A computer reset generally happens after a fault or when the computer program goes off and gets lost and starts executing bad commands somehow. However, in the field of machine control, and the Leap device is in fact a simple machine, Watchdog timers are often used not to reset the computer after some problem, but instead are used to make the processor repeat a control loop periodically. Every time the Watchdog timer signal comes in, the processor starts executing its program at the beginning. And we can surmise that that is what's happening here. The processor on this thing probably begins sending data it retrieves from the vision sensors to the computer every time it gets a Watchdog signal generated by the timer circuit connected to this crystal. This kind of program looping, by the way, is what takes place in dedicated industrial computers that are called programmable logic controllers. All they do is continually look at sensors, switches, and other inputs, perform some kind of function based on what they see, then go back and look at the inputs again, over and over. So in a way, the Leap designers have used the Watchdog timer function to create an extremely tiny version of a programmable logic controller. But let's move on so our little video doesn't get too long. Flipping over to the other side of the top board, we see several interesting components. Here are two 470 microfarad capacitors, and here is a 30 volt P-channel MOSFET. The MOSFET is rated to handle currents exceeding 11 amps at room temperature. There's only one operation on this board that would seem as though it might require currents anywhere near 11 amps, and that would be to drive the 3 infrared LEDs that illuminate your hands waving over the device, and the little LED on the side of the device that serves as a sort of on-off indicator. So we can surmise that this lone beefy-looking MOSFET serves as the LED driver. Now, a question you might ask is whether each LED has its own drive circuit, in which case you'd need at least 3 drive transistors instead of 1. But you can see from other videos out there about the LEAP device that the infrared LEDs are pulsed on and off, and they all seem to be switching on and off at the same frequency at the same time. This leads us to believe that there is only one driver transistor handling all the LEDs. Now, to get the LED on-off behavior, there's probably 2 possibilities. The driver transistor could be driven by the processor, toggling its input on and off. That's certainly the most likely scenario here, but there's also a chance the LEDs would be driven by some kind of discrete free-running oscillator. In the videos that are out there, you can actually see the LEDs turning on and off, so the oscillation frequency is relatively low. And one way to synthesize an oscillator for relatively low frequencies like that is with an RC oscillator. So we might theorize that the 2 chunky capacitors over here are part of the oscillator, but really, I don't think so. The capacitors in the RC circuit wouldn't need to handle a lot of energy, and at least to my eye, these look oversized for that kind of job. So I'd have to say I'm not sure why these 2 capacitors are really here, and I'd invite viewers to chime in on this point. One final idea before we leave the topic of the LEDs is why the designers of the motion controller chose to pulse the infrared LEDs on and off at all, rather than just let them illuminate the target all the time. On that, we can be pretty sure the reason is to help discern the targets from other sources of background infrared light, such as an oven or something like that. Most likely, when the software detects motion, it first filters out objects not illuminated at the LED on-off rate, and it would be a relatively simple software filter to implement that as well. And that brings us to the next major component on this side of the board, the USB controller. This chip is actually built on a 32-bit ARM9 core, originally from ARM Holdings. When you find out that this thing can handle 375 megabit per second data transfers to the USB interface, you start to understand why LEAP decided to use it. There's a lot of data coming through from the 2 vision sensor ICs, and this thing has the capacity to handle it. The image sensor data comes into the processor through a parallel programmable interface called GPIF2. GPIF2 handles up to 32 data bits in parallel. In the case of the LEAP device, those data bits are coming from 2 vision sensor chips. Vision sensor data comes onto the circuit board from the 2 vision sensor ICs via this 44-pin high-density connector, which seems to be from Molex. One thing we can't discern just by following traces on the board and looking at components is how that vision sensor data is configured. I don't know whether each vision chip sends 32 bits of data and the processor interleaves between them, or whether both vision sensor chips send 16 bits of data simultaneously and the processor reads them both at the same time. This is another point on which I hope viewers may chime in on, particularly if you have some insight on how this might happen. We'll make just a couple more comments before we leave the discussion of the USB processor. First, note that basically all this processor does is format data coming from the 2 vision sensors and send it serially back over the USB connection to the host computer. And that's basically it. The processor isn't doing any analysis of that vision sensor data at all. All the magic of interpreting the hand motions and gestures happens in the software running on the host computer. Second, I don't know how well you can see the details on the small circuit board, but I hope you can get a feel for the workmanship here. There are a lot of super small surface mount components on this board, and it isn't a simple board either. It's at least 3 layers. So if anyone from LEAP is watching this, I'd say good job on your circuit board work. Also, I'll make a comment about what component you don't see mounted to this board. There's no MEMS accelerometer, as you might find on a Wii board or something similar. The LEAP controller isn't sensitive to its own motion other than with respect to whatever objects are floating 2 feet above it that are illuminated by its infrared LEDs. I mention this because there's been some talk of using this device as the basis for virtual reality headsets. If that happens, I would think those headsets might have to incorporate a separate accelerometer somehow to get the kind of realism that's come to be expected from VR equipment. Finally, let's get down to the 2 vision sensor chips themselves, here and here. Of course, the motion controller uses 2 vision sensors rather than 1, so it can implement stereoscopic vision and thereby discern depth. The 2 chips mount on a back circuit board that connects to the top board via the 44-pin connector. They are also heat sinked to the back of the metal enclosure through a light piece of adhesive fabric, and we can see our heat sinking there. There are no markings on these chips, so we can't really see who made them, but maybe the most interesting thing about the 2 vision sensors are their lenses. LEAP says in its literature that the device can see a field that is 150 degrees wide. A close look at the lenses reveals how this happens. They seem to be fisheye lenses. You might be able to see that from taking a close look at the side of the lens. And of course, fisheye lenses see in a wide panoramic or hemispherical mode. Just the thing when you want a 150-degree view of the surroundings. So there you have the LEAP motion sensor. It's quite a nice device. We've made a number of educated guesses about how it works based on what we see on its circuit boards. But they are, of course, just educated guesses. If you've got other ideas how things are done on a LEAP sensor, we invite you to chime in on the comments section below the video. And thanks for watching.